Uh, okay, guys. In this lecture, we will study stiff ordinary differential equations, and we will also see, the systems of stiff ordinary differential equations, and we will see a couple of, numerical techniques in order to, deal with these kind of problems. Let me tell you, you know, a background for these, a special kind of ordinary differential equations. Okay, so as we have seen, in the previous lectures, that the solutions corresponding to the ordinary differential equations, they contains basically, elementary functions. So elementary functions like, for instance, logarithmic functions and trigonometric functions, for instance, and similarly, exponential functions as well. Okay, let's pick one of them. For instance, you have, dynamical system, which is basically, let's say, a second order ordinary differential equation, and you solve it by using some, let's say, analytical approach. And let's say you got its two solutions which are exponential in nature. For instance, let's say one of the guy is, e to the negative t, and the other guy is, let's say, e to the negative 3t, for instance. Okay, and then you can give a look at both of these two functions which appear in your solutions, while paying attention at the time t. So for instance, as time t is very large, then you will see that one of them will decay very faster. Okay, for instance, e to the negative 3 t will decay very fast, and it's more negative. And then the other guy, e to the negative t, will dominate. Okay. So let's say now, you divide, the time interval. You have your solution, then let's say in two-dimensional, plane, and the horizontal axis you have time axis, and you can divide, time axis into several, sub-intervals, and let's say you choose two particular, sub-intervals, and then you can see that, across one sub-interval, your solution corresponding to, ordinary differential equation is packed. So what I mean by pack here is, the solution, moves very slowly, and it takes, very small steps in order to do this. And of course, on the other hand, your solution is, the behavior of the solution is very fast. It can move faster compared to, the previous, let's say, the sub-interval where it was slow. And in this particular case, it will take, you can say that the steps which are, of course, larger compared to, the other case. So once, the solution is packed, it moves slowly, and of course it takes a lot of, time steps in order to do this. Then it means that across that particular interval, you will have basically stiffness. Okay, so this is one of the key things which is about the stiffness. Okay, so here are the contents which I will try to cover in this lecture. So first we will consider, maybe ordinary differential equation, simple ordinary differential equation, and we will see its definition. Of course, I'm talking about the stiff ordinary differential equation, and we will try to understand them with the help of two model problems. Okay, And then in the second part, I will try to understand stiff systems of ordinary differential equations. And again, I will consider two model problems, and I will use explicit and implicit Euler methods in order to understand these the stiff systems of ordinary differential equations. And then I will share with you some data which will give you more information about stiff systems. And then finally, of course, there are a few exercises, if you like, you can try them. Okay. Okay, so let's begin with our first part. So as I told you earlier that, stiffness is basically of course, it's a subtle, a difficult concept when you talk about, the behavior of the solutions of ordinary differential equations. But it is, one of, you can say that, the important concept, and, an ordinary differential equation, especially when you, talk about, the numerical solutions of ordinary differential equations. In mathematics, a stiff equation is basically a differential equation for which certain numerical methods they are basically unstable, unless of course, if you take the step size, which is extremely small, and in that case, maybe you are in a good position actually. Okay. The stiffness of ordinary differential equation, the system of ordinary differential equation, not only depends on, you can say that the differential equation under consideration, but it also depends on the initial conditions for that particular problem, and then of course it also depends on the numerical methods that you develop in order to deal with this kind of problems. Okay. We say that a problem is stiff, if solutions being sought varies slowly. But what about, let's say, the solutions which are nearby? And then, of course, the solutions which are nearby, they can vary rapidly. Okay, so this is what I told you. At the initial stage that across subintervals, it's possible that across some intervals, if you take very small, time steps, then your solution will move very slowly compared to if you take the larger step size. Then of course maybe you can have the solutions which vary very rapidly. So it can be kind of oscillations, so on and so forth. Okay, thus your numerical method must take small steps in order to obtain some better results. Okay. Yes, stiffness is basically an efficiency issue. We will not study this in this particular lecture, but of course it's something which is very interesting, and one can cover it at a later stage. Okay. Now the point is, if you're not concerned with the time which is taken by your numerical technique in order to deal with stiff ordinary differential equations, then of course you're not talking about basically stiffness. So you have to pay attention on your numerical method. So of course you have to develop an efficient numerical method, which is of course maybe cheap but take less time in order to deal with the problem. Non-stiff methods are also, widely available in order to deal with stiff problems. But the only thing is, they will take, long time in order to solve some, let's say, a stiff problem. Okay. So now we will see that what is basically a stiff ordinary differential equation. So okay, let's just begin with a very simple case, and we say that we have this first order ordinary differential equation. You can have an equation in this particular format as well, where this guy is basically a mass matrix. Okay, and we say that this problem, or maybe this guy, is basically stiff when the exact solution corresponding to these problems, they include terms which decay exponentially, and of course eventually they reaches to zero. And this is possible when you take time to be very large. Of course you want to study long-term behavior. Okay, so as an example, we can consider, let's say, this guy to be one of the solution of this, let's say, the differential equation. And now you have this guy, the coefficient of t, which is, let's say, c. It's a very large positive number. It could be a very large positive number. Okay, because if you take its k derivative, so you will get an expression like this. Okay, and now the point is, you see that because of this factor, the derivative that decays to zero, it takes a few time. Of course it's very slower compared to this guy when t increases, because of the presence of this factor and the front of this exponential function. Okay, there are actually Matlab solvers which are available in order to deal with stiff ordinary differential equations. So mainly we have basically solvers for stiff and solvers for non-stiff ordinary differential equations. So we have you can say that stiff solvers and non-stiff solvers. Okay, so for instance, for stiff ordinary differential equations, we have the solvers like this. Let's say ODE 15s, ODE 23s, and then so on and so forth. So these are for stiff ordinary differential equations. Okay, so for instance, if you take a certain differential equation, which could be a stiff differential equation, or even differential algebraic equations, so you can solve them with the help of this ODE solver. Okay, and similarly, if you have stiff differential equations, and you can use lower order method in order to solve them, and you can also use this Matlab solver as well. Similarly, for instance, over here, now you can use ODE 23TB in order to solve stiff differential equations, and then this thing is basically based on the top of the trapezoidal rule and the backward differentiation formula. Okay. We also have the non-stiff solvers for ordinary differential equations. For instance, here ODE 45, ODE 23, and ODE 113. So these solvers can use when you have basically non-stiff differential equations. Okay, so in all these cases you will see that you have non-stiff differential equations, and you can use these solvers. Then it of course depends which one is better. For instance, norm practices, you can start with this, and maybe if you're not happy with that, you can choose some other guy. Okay. Okay, let me say a few words about these solvers. Okay, so yeah, for instance, if I just pick one of them. Let's say ODE 45, and as I told you earlier that ODE 45 basically, solve nonlinear, non-stiff differential equation. And here it's syntax. So you can use ODE 45 to attack some particular, let's say, stiff ordinary differential equation. Okay, and here is the description of this syntax. So for instance, here this guy is basically a function that will help you to evaluate the right hand side of your stiff ordinary differential equation. Then you can introduce this guy at the time step, let's say from T0 to Tf. Okay, and then you can integrate your differential equation with this particular time interval. And this guy over here basically represents the initial conditions corresponding to your differential equation. And then you can also use this argument options, and you can do it by using this function which is ODE set actually. So I'm not going to tell you more detail on ODE set, but of course, I mean, if you just click it, you can read a lot about this guy as well. Okay, and then I mean you can also study some extra information. For instance, at the next step, I can for instance find these guys, the even functions, which will be 0 actually. Okay, so in order to do that, of course, I can as an output what I will get is basically the time event, which is this guy TE. Then of course YE, which will basically tell the solution at that particular time event. And similarly, this guy over here is basically the index of triggered event. Okay, and then finally, of course, I mean, you can go towards the solution of ordinary differential equation. And this guy over here basically returns a structure. Of course, you have to use this devel. So again, I'm not going to enter into the detail about devel, but of course, I mean, if you go to the Mathworks, I will share, of course, the links and the details where you can give a look. Okay, and either to evaluate your solution of ordinary differential equation at any point in this in this particular interval. Okay, so for instance, we can take one simple case. So here is a simple ODE, which is y prime is 2t, and then you can take some time interval and initial conditions, and if you write down this Matlab syntax and you call it, and then you will see that you will get basically this kind of the solution. So the behavior of the solution of this differential equation is basically this guy. So it seems that it's basically maybe an exponential function. Okay, and then of course there is a lot of detail about the non-stiffness, so on and so forth. So I'm not going to enter to that particular direction. Okay, and similarly, you can study these guys as well. For instance, ODE 45, ODE 23, ODE 113, and these stiff solvers as well. So you have to click each and every one, and you can study a lot from this page. Okay, great. Okay, so now I go back, and okay, so I was here. Great. Okay, now the point is, I mean, you can see that which ODEs, I mean, which solvers is better compared to the other one. So for more stiff, for most the stiff ordinary differential equations, so it's better, I mean, if you use ODE is 15s, because it performs in a much better way. Okay. Also, let's say these the stiff solvers can be more efficient for the problem that permits a crude error tolerance. Okay, so I'm not gonna enter again in this particular discussion, but of course these are helpful when you deal with the stiff ordinary differential equation. Okay, the problem that the stiff differential equation poses that the explicit solvers, for instance this guy, are very slow in order to achieve the solutions. And I mean, you can realize it if you attack some kind of the stiff differential equations with the help of these solvers. Otherwise, it's I know it's complicated to understand this concept, but of course for this you need to, or you have to play with both these stiff and the non-stiff ordinary differential equation solvers. Okay. Yes. And let's say this guy is basically it's slow for for your ordinary differential equations. Then of course instead of this you can maybe use some other non-stiff solver. For instance, this one, and for instance this one. So for instance, if you don't want to use this, maybe you can try this, and then you can try this. Okay. Okay, let's take our first example, which is a stiff van der Pol equation. So as you know very well that basically a van der Pol oscillator is of course a nonlinear system. So here is a nonlinear ordinary differential equation which will describe the dynamics of the van der Pol oscillator. I take the simple case when there is no external force, and this guy y1 could be, let's say, the position coordinate, and this fellow over here is basically a scalar parameter. It's a basically damping factor, and this will indicate basically the non-linearity of the damping and the strength of the damping as well. Okay, so we can see that this second order non-linear ordinary differential equation, which is basically the van der Pol equation, and of course it is a stiff ordinary differential equation. And if I just pay attention on this damping parameter, let's say in the absence of this damping parameter, your van der Pol equation will reduces to this the second order ordinary differential equation, and this is nothing but it is a simple harmonic motion. Okay, and you can one can also study this second order ordinary differential equation as well. Okay, and in the presence of damping, your van der Pol equation basically reduces to a system of ordinary differential equation which are non-stiff. Okay, and you can use some non-stiff ODE solver in order to solve your system. For instance, ODE 45. Okay, and now the point is, when the damping parameter is present, of course, let's say it can have the different values. It can have even the maximum value. And the point is, when your damping parameter increases, then you will see that your solutions near the origin becomes unstable actually. Okay, then after a very long time, of course, your solution will start oscillating. So for instance, you can see over here, if I take a damping parameter, this is 0.2, I increase it and I further increase it, and then you will see that if I just check the behavior of the solution, then you will see that near the origin, it is, of course, it is unstable. And then, after a very long time, your solution will basically, oscillate. And over here, basically, I have, the derivative of, this guy. Okay, and this shows that, of course, again, I mean, the solution is unstable over here, and then, you will have this kind of, the behavior for, the solution of your van der Waals oscillator. Okay, and of course, I mean, when you increase this guy, I mean, further, then you enter basically to a limit cycle actually. So this is, a limit cycle. And similarly, for instance, if damping parameter is more larger, then you will see that you will have a more instability, around the origin, and you can see, for instance, over here as well. So compared to this guy, I mean, over here, of course, you will have, more instability. Okay, so let's say if I choose damping parameter to be, let's say, 1000, then you will see that the solutions of the van der Waals equation basically changes dramatically actually. Okay, of course, you take a very large time. And of course, you can use, I mean, ODE 15S instead of, I mean, let's say ODE 45, because it will perform much better. Okay, we can rewrite van der Waals equation as a system of, the first order ordinary differential equation by making use of this substitution. Okay, and if you do this, you will get, this kind of, a first order ordinary differential equation system. So this is, of course, a stiff system. Okay, and now the point is, I mean, I can use this, this function with this damping. Okay, and I can write down, this small, Matlab code, and I can call this ODE 15S, and I can construct, let's say, this initial condition vector and this, the time interval. So I take a large, number of points. That's about 3000. Okay, so you call your ODE 15S and introduce the things which are required. Okay, and this is your, of course, the time interval, initial conditions. You can plot them and title, and then of course you can, label your both axes. And if you do this, you will see that the behavior of the solutions of the van der Waals equation looks like like this actually. But the point is that you can see that, let's say our this interval, let's say if I take 0 to 500, and you can see that over here we are happy because our solution, let's say, move faster compared to, for instance, over this particular interval. Okay, so over this interval, you see that the solutions are basically, they are packed, and the flow is very slow actually. So it means that we have stiffness. So you can have stiffness at the different time interval. For instance, I can only have over here, but here I'm happy actually. Okay, it's a fast flow. Okay. For example 2, this example is given by Champin. He is basically, one of the author of the Matlab ordinary differential equation suite. Okay, so please visit Matlab and try to, give a look at ordinary differential equation suite, and you will, of course, study, the Matlab solvers for stiff and non-stiff ordinary differential equation. Okay, and the example is very interesting actually. So let's say, I mean, you light a match. Okay, then what will happen? Of course, I mean, the ball of flame will grow rapidly, and then it will, reaches to a critical size. So for instance, you can consider this situation. Although, I mean, at the moment, I mean, we can't see, you know, a ball, but, you know, it's possible that, you know, at the initial stage or at some stage, you know, maybe, you know, this flame will be basically, it will look like as a ball actually. Okay. Now, but the point is, I mean, you know, the ball remains at a critical size. Okay. Of course, I mean, you know, this is possible because, you know, the amount of oxygen which is consumed by, you know, combustion inside the ball, that will balance basically, you know, the oxygen which is available through the surface. Okay, so so here is, you know, the simple model which describes basically, you know, the flame propagation. Here, this guy basically, you know, represent, you can say that the radius of the ball actually. So your function y basically represent the radius of the ball of the flame actually. Okay, and you can see, I mean, from the construction that these and these guys, they represent, you know, this guy represent the surface, and this is the volume, and then you have this, you know, the initial condition that. So this guy, this parameter over here, basically, you know, the radius of the ball at the initial stage. Okay, let's say, I mean, at time t is equal to 0, you know, you have the ball of the flame, but, you know, its radius is, let's say, this number delta. It could be very small. Even you can vary it. It depends on the time t. So, for instance, you can see over here that your t has kind of, you know, inverse relation with the delta. Okay, so I mean, what will happen with the flame? Eventually, you know, it will disappear, but after a large timeline. Okay, so you can see over here, I mean, as you move further for a large time, of course, this guy will disappear. It's clear from this information. Okay, so as I told earlier, that delta is the initial radius of the ball, which is small. This function basically represents the radius of the ball. And these two guys, they are, of course, I mean, the surface and the volume, respectively. Okay. Our target is basically, you know, to seek a solution over a length of the time t, which is, you know, inversely proportional to the initial radius of the ball. Okay, and if you use, you know, this non-stiff ODE solver, which is ODE 45, and of course, I mean, you can use something else, but let's say we use this, and if I choose that, you know, this delta is not very small, then the problem is not very stiff actually, because stiffness will depend, of course, on this delta as well. Okay, for instance, let's say I choose you know, the initial radius of the ball, which is, let's say, 0.01, and I choose some relative error, let's say 10 to the minus 4, and then I can, you know, write down my given differential equations, and I introduce the tolerance. I use ODE 45, and you know, I take help of the Matlab, and then you will see that the plot of the solution will start from 0.01, and it will grow at a modestly increasing rate until, you know, your time approaches 100, which is basically 1 over delta. And after that, what will happen? After that, basically, you know, your solution will grow rapidly actually. Okay, and then it will reach this guy 1, which is the maximum value, and then it will remain stable for all, you know, time. It will move very slowly. So, for instance, over here you can see the behavior. So, at time t is equal to, you know, 100. So before it, we are an IRP mode because you know, the solution is not packed. We don't have, you know, more stiffness or much stiffness, you can say, over this particular interval. But after that, you know, it will increases. So you can have basically this, a monotonically increasing behavior of, this trajectory, which is basically solution. And then it attains this maximum value 1. After that, it remains stable. But the point is, after this point, it will move very slowly because of the stiffness. Okay, if you use, let's say, this ODE 45. Okay, let's say maybe we can use, Matlab. Excuse me. Okay, if I use Matlab and I take, let's say, delta to be 0.01, which is, the initial radius of the ball, and then, I can, of course, call excuse me, I have this Italian keyboard actually, Okay, so then, of course, excuse me, I need to call, the equation, let's say, which is basically, let's say, y squared minus what? Y cube. Okay, cool. And then I use, let's say, ODE's, I use ODE, ODE 45 salary. Okay, but let's say I introduce tolerance. I use ODE set function. Okay, and I take the relative tolerance and how much you want. Let's say e to the minus 4. You can vary, no problem. And then you use, let's say, ODE 45. Let's play with ODE 45, and you call the things which are needed. And what is your time interval? Let's say, so we have to delta. Delta and then odds. Okay, so it's in the previous step. Okay, you're done. Okay, you see, for instance, here now. Of course, after, let's say, at 100, you have this basically abrupt change. And then this guy goes to 1, it will remain stable. But you see over here, we have a stiffness. Here, the things are, are fine. We are happy, actually, but not here. Okay, good. Now the point is, if I to see the stiffness in action, so let's say I play with delta, actually. So I increase, the initial radius of the ball. Then let's see what will happen. How much? Let's say the 3 times. Okay. Let's say this is 0.0001. I call ODE 45, and then let's see what will happen. Wow. Now you see that, of course, so at 1, you have again this kind of, behavior, but of course you have more stiffness actually over here. So you will get, of course, more stiffness compared to this guy. And this was kind of, okay, monotonically increasing behavior. But here, you see that you go like, you see that you have a different behavior actually. Okay, over here. So yeah, okay. For instance, you can see. Yeah. So if I use delta to be more small, let's say. Okay. this guy, and then I call, this guy, and you will see like this. Wow. I mean, now the point is, I mean, you see that, after this interval, your solution moves very slowly, but at the initial stage, you have seen that this guy, moves very fast, because over here you have a stiffness actually. So I can stop it by using this button, and then maybe I can see that actually what's going on over here. Okay. Okay. Yeah. Excuse me. So I can zoom in, and I will see that actually what's going on over here. Okay. So this is the stiffness part. Actually, when I choose this guy, let's see this guy, stiffness and action. You see, I mean, yeah, over here. So this is the stiffness, and of course, I mean, it will take very small time steps. Okay? The solutions are basically packed, and if you zoom it more, so you will see that, for instance, responding to this guy, okay, and the neighborhood, of course, you will have entirely different behavior of the solution. So solution, something, let's say over here, it can increase, maybe sometimes it can decrease. So you have this kind of strange behavior for the solution, and this is basically the stiffness in your problem. Okay, good. Okay. I mean, in this case, you see that your solution basically reaches to this steady state, actually. Okay, so it reaches to the steady state, then of course your problem becomes more stiff, and the reason is very simple, because your solution is rigid, actually. Okay. Now, if you take, I mean, this point where you got basically this, the steady state. And then, if you just give a look at the solutions which are nearby to this point, of course, your solution will either, increases or decreases rapidly towards your, desired solution, actually. So this is what I told you earlier, okay? Now to our flame example, if I use this, the stiff ODE solver, let's say ODE 23S, S is for stiff, basically, and I choose, this delta, I use this guy, then what will happen? Can you guess that what will happen? If you use the stiff solver. Then of course, I mean, the things will be entirely changed. Boom, over here, I mean, you can see that you don't have more, the stiffness, actually. So kind of, you want to get rid from the stiffness. Okay. So for instance, I mean, if I go back, let's say I use delta is the same. Excuse me. ODE 23S. Then let's see what will happen. Wow. So you see. So you see that, I mean, over here, you get rid from stiffness, actually. So, of course, the time steps, they increases, and the solutions are apart. And you feel basically happy. Okay. Great. Okay. So we can say something more about ODE 23S and ODE 45 in comparison, because you see that ODE 23S takes fewer steps compared to ODE 45, okay, in order to solve your problem. Now the point is, I mean, this stiff solver will take only 99 steps, for instance, this particular example, and it will uses about 412 function evaluation. But on the other hand, I mean, this guy will take, 3,040 steps, while, it will use, 20,179 function evaluation. Okay, so you can see the difference, I mean. Of course, this is, exercise, and unfortunately, you have to do it. But the point is, I mean, if you solve, this problem analytically, then you will see that, and the solution is, lambda W function will appear. This is a quite famous function. So your homework is basically try to solve this, stiff ordinary differential equation. Let's say this, excuse me, I mean, let's say you try to solve this, the flame problem, and then in the solution, I mean, you will see this character and try to understand it. Okay, good. Now we move towards, the system of the stiff ordinary differential equations. Okay, so I take a very simple situation. I consider this system where this guy is itself basically a positive, parameter, and I have this initial condition. Okay, so this is basically, a stiff ordinary differential equation. Since it is a stiff ordinary differential equation, and this differential equation model is actually something which decay in time. For instance, you can, for a better understanding, you can take, the mass of some radioactive element, and you know that with the passage of time, the change in the mass is basically, related with the original mass, which is, initially present. Okay. Similarly, I mean, you can take this example. For instance, you invest some money in the bank, okay? But the point is, the bank can, lose your money at a certain rate, okay? And now, you can study, this kind of, the stiff ordinary differential equation, that what you will get after a long time. Okay, so yeah, this is another interesting example. Although, I mean, you can say that methodologies are available in order to, deal these kind of problems. Okay, but of course, you can also, involve stiff ordinary differential equations as well. So for this particular problem, if you use some, available analytical approach, you will get the exact solution, okay, which is this exponential function. And basically, we are interested in a property, let's say P, for the solution. And the property says that, the long-term behavior of your solution is that, it, let's say, decreases, let's say, asymptotically. Of course, I mean, you go back to 0 actually, okay? So we can use, forward Euler method for this purpose, okay? So the forward Euler method says that, the informations, available at these points, so they are basically, let's say, can be, studied with this expression actually. So this guy is nothing but this is, the step size. So just imagine, the horizontal axis and you got, let's say, T0 and T1. So it's a difference, T1 minus, let's say, T0. We can take it, positive, if you like. And this guy is nothing but, this guy is the derivative. And you can play with this equation. Of course, you can take some initial condition as well, and you can write this above expression in this particular form, because this x prime is given actually. This is your original equation, and you can rewrite it in this particular form, okay? And now you can make use of induction and then the initial condition, and this expression can be written in this particular format. Okay, so then eventually, I mean, you will get this expression. Okay, now the point is, I mean, since our goal is, the property P to be remain preserved. Okay. And for this, yeah, of course, I mean, our goal is basically, as this guy, increases, then, your solution basically, let's say, it has asymptotic behavior. It will basically, decreases. And you can ask a very simple question that, well, okay, but when this will happen? Okay. So the constraint is that, this expression, this fellow, in terms of, the absolute value is basically strictly negative. Okay, this is strictly less than 0. It's negative actually. And then if you play with this inequality, you will get, the conditions and this step size, which are something like this actually. Okay, and you see that if you vary, I mean, this guy in the denominator, then, of course, something happens in your step size. So it means that, you have some kind of, condition on, this guy H actually. So we say that, well, I mean, our numerical method, which is basically, this guy, the forward Euler method, basically it gives us stability, but it's kind of, the conditional stability actually. We're going to have some condition, this step size, time step, you can say. And then we ask this important question that, okay, you have this, conditional kind of stability, but can you just remove this condition to have A to be very large? Yes, it is highly possible, of course. I mean, and for that, I mean, maybe one can use, this implicit Euler method, and this will help you to, improve the stability. Okay, so here is the implicit Euler method, and the key point is, I mean, your unknown guy, which is, let's say, this one, but on the right hand side, I mean, you see that the information given over here also appear over here. Okay, so you can rewrite it, of course, it's not that difficult, and then you will get an expression for, let's say, these guys. You can make use of induction, and you will get, this kind of expression. And of course, you can use initial condition, and this guy will also, disappear. And then for the stability, I mean, what you want, of course, you want that, when this fellow is very large, okay, then this fellow are your solutions basically, let's say they goes to 0. So you're going to have a basically, it depends on the behavior, but let's say you move towards 0 actually. Okay, but this requires the fact that, the absolute value of this guy is strictly less than 1 actually. Okay, and we are happy in this case because if you just play with this, strict inequality, then you will see that, these two guys are basically positive. So there is, you can say that, no condition on your step size actually. Okay, so once you have no condition on your step size, then it means that the things are smooth, and you will have basically, stability, but unconditional stability actually. Okay, so there is no condition. Okay, so to understand it better, so we consider, a 2 + 2 system of stiff ordinary differential equations. Okay, and we consider initial conditions. Okay, and this linear system of stiff ODEs can be written in the matrix form, and then you can just do analysis for this coefficient matrix. I call it as the matrix A actually. Okay, and the point is, I mean, for stability, you can just compute, on the spectrum of this guy. So, for instance, in this case, the spectrum is negative actually. So you have these two values. Okay, and now the point is, I mean, you can study this, the condition number of your matrix. The condition number of your matrix basically will tell you, either your system is basically, ill condition or it is a well condition. For instance, if you are lucky enough to have the condition number, which is, a small number, let's say maybe 1 or close to 1, then maybe you are in a happy situation actually, and you will have, well conditioned system. On the other hand, if this guy is a large number, for instance, over here, it is a large number. So 39 is a quite large number. Then, I mean, you are not in a good situation. You will have actually, ill-conditioned system. Okay. So ill-conditioned systems, I mean that, if I perturb system, let's say at a small scale, then of course, I mean, the solution of your system will, change, dramatically. Actually, there will be a large change, and the solution corresponding to your differential equations. Okay, so you can just, maybe consider the example of, the fragments in a room actually. Okay, and a condition number is mathematically, it's just, the ratio of this, relative, the absolute value of the relative stretching. You can say that, the absolute value of relative shrinking actually, because then the max will tell you, the stretching, and this will tell you, the shrinking element. Okay. So if you use some analytical method, so the solutions for this, the stiff ordered differential equation is something like this actually, and you can see that you have these, exponential functions which contains basically the spectrum. Okay, and then you can have, these observations, and the observations are, I mean, both solutions, let's say x and y. So of course they will have, this asymptotic behavior for large time. Okay, so at a large time you will have basically this asymptotic behavior, and these two guys, this guy and this guy, of course they will decay. Okay, and you will see that, I mean, this guy, I mean, it will decay faster compared to this guy when t is very large. So it's obvious, it's clear if you just give a look at these two expressions. Okay, and this means that, for large t, this guy will dominate, and then it's possible that this guy, kind of disappear from your solution corresponding to, the stiff system of ordinary differential equation. We call this guy as a transient term because, now, there is only one line in the jungle, which is basically, let's say, e to the negative t. Okay, because this guy, although this guy is there, I mean, but the point is, it has a very short term influence on the solution. But the point is, you cannot neglect it. It doesn't mean that, only lion can, live in the jungle. There are other animals as well, and they can create some problem or trouble at some time. Okay, good. And if I use, the forward Eilers method for this particular system, then, I can write down my solution in this particular format. So it means that if this information, yes, excuse me. Yes, so the forward Euler method for this system basically takes this form, and the initial conditions are over here, and this is, of course, again, I mean, a little exercise that if you use forward Euler method for this stiff ordinary differential equation, then your solution will appear in this particular format, actually. So you will get the terms like this and the terms like this. Okay. And now the point is, I mean, of course, your goal is basically, you know, for large and, you know, both of these two solutions, they have, you know, this asymptotic behavior. Okay. But now the point is, I mean, there are two conditions basically. So the first condition is that for the stability, to study the stability, so you have these two conditions. So the absolute value of this guy and the absolute value of this guy, they are basically less than 1. Okay. And from these two, you know, the strict inequalities, you will get, you know, the expressions for this time, the times, let's say the step size. Okay. But you see that, I mean, this guy is much smaller than this guy. So this means that, you know, you will have, you can say that a stability condition basically. Okay, so this guy basically here becomes a stability condition, and of course the conditional stability. Okay, so it means that we have basically a conditional stability. Okay, this term is basically, you know, is a transient term. Okay, because as you can see, this guy is much, you know, smaller than this guy. Okay, so this gives us basically, you know, a stiff system of ordinary differential equation. Okay, and the system, you know, has, you know, different rates and frequencies, with the help of which it varies. Actually, its solution basically varies. Okay, and now to improve the stability, one can use, you know, implicit Euler method instead of, let's say, the explicit Euler's method. Okay, so if you use, let's say, the implicit Euler method, so here is what I have used is basically the backward Euler's method. So you can see that the information available here, they are also, you know, appearing over here, and the same is true for, let's say, this guy. Or you can say that both of these two guys, they will, you know, appear on the right hand side of your these equations. Okay, so these guys are unknowns actually, xn plus 1 and yn plus 1 solutions that you can say that these points. Now I can make use of, you know, a linear algebra, and then, you know, I can study, you know, the analysis for the stability condition. So for instance, you know, I can introduce this vector u, which contains, you know, the components of the solution corresponding to your stiff ordinary differential equations. Okay, so for instance, I can pack these two guys over here, and then, you know, the coefficient matrix will emerge basically from here. Okay. Now, the point is, I mean, you know, what do you want basically? Well, I want that, you know, un plus 1, basically, you know, this guy, you know, must have asymptotic behavior actually, as n is very large. Okay, so I can, you know, write down this system and the vector form as following. Okay, you can see that this guy is packed over here, these guys are packed over here, plus h, the step size, times, you know, your coefficient matrix, and then both of these two guys are packed, you know, and the vector un plus 1 actually. Okay, so they are here. And furthermore, I can play with this, you know, equation, and I will get an expression for this vector in this particular form. Okay, and then I can further, you know, play with this, and, you know, the expression for the components, let's say xn plus 1 and yn plus 1 can be written in this particular format. Okay, and then of course I can focus on this matrix inversion. So this is my aim basically. I want this vector to be to have this asymptotic behavior as n is very large. Okay, and now for this, I make use of the vector norm, because that if I use the norm, this is possible, of course, when maybe both of your solutions, uh, they have this asymptotic behavior actually. So for instance, if both of the components are, exactly zero, then I am in a happy mode. Okay, and if we use, let's say, the vector norm, you can use any vector norm basically. And then, this expression can be written as the following. So you see that I take this. So if, I apply the vector norm, and then this is a, matrix time vector. So I can use the property, and I will arrive this step. So this we have already seen in the course of, linear algebra and advanced linear algebra. Okay, and then the point is, I mean, for this guy to be, to have, asymptotic behavior, the point is, I mean, this guy must be strictly less than 1. Of course, it should be, a very small number. Okay, and what does that mean? I mean, so that means that, I can, let's say, use, I mean, in order to do that, I can use some vector norm, let's say maybe L2 norm or some of the norms. So for instance, I use L2 norm because, it's deeply related with the spectrum of the given matrix actually. Okay, so how we define the matrix 2 norm is as follows. So you have to, compute the spectrum of the given matrix, and then you choose, the maximum eigenvalue from that spectrum. Okay, so this expression can be written in this particular format because this is, the inversion. That's fine, and this can be written in this particular format with this guy to be, the minimization problem. And over here, basically, I have, the eigenvalues of this, the polynomial expression actually. And meaning the result from the linear algebra that if you have, the eigenvalues of this polynomial expression, then it can be written as, a polynomial expression of the eigenvalues of that matrix. Okay, so and then, I want that this guy to be less than 1. In other words, you can say that this guy is, strictly greater than 1. And yes, we are happy because, I mean, both of the eigenvalues, let's say the spectrum is negative actually. So it's a negative 39, it's a negative 1, and then we are happy actually. So it means that we don't have any condition on our, the step size, and we have, kind of, unconditional stability for our, system of ordinary differential equation, which are stiff actually. Now, the advantage of the implicit method is that it's stable all the time for, large step size. You can take the large step size even, no problem, and you will get all the time the stability. And another advantage is that, in order to reach the final computing time, it will take, fewer steps compared to the explicit method. But at the same time, it has disadvantages as well. So for instance, for the linear systems, I mean, the point is, I mean, we have to solve, a system of linear ordinary differential equation at each time step actually. So this is, one of the disadvantages of the implicit method. And it becomes more complicated when, instead of a linear system, we have, a non-linear systems. So in that case, you need to, adopt first Newton iterations at each and every step actually. Okay, and this is not that cheap actually. And of course, you have to choose some suitable initial guess near, a solution in order to have the convergence. And of course, I mean, doing doing this is very expensive actually. Okay. So this means that we have to be very careful if our problem is, stiff in nature. Okay. But first, we have to check that how much, stiff our problem under consideration is basically. Okay. And then you ask a question to yourself that, can I tolerate its stiffness? Okay. While let's say you have the small time steps, and if yes, you can live with it, it's fine. Otherwise, of course, I mean, you have to do something else actually. Okay, but if you can live with the, let's say, with the stiffness while having, the small time steps, then, try to live with it. Otherwise, I mean, you have to do all this kind of analysis actually. Okay, otherwise you have to use, let's say, the implicit Euler methods, and that involves basically, the computation of the fast Newton iterations at each and every steps. Okay. Now for extra reading, I would like to recommend you some, material. So you can visit this website. This is basically Scholarpedia, where you will see the materials for the stiff systems, which is basically given by Professor Lawrence Champagne from the Department of Mathematics at Southern Methodist University back in United States of America. So here is it, his homepage. If you just copy paste this or sort this, so you will find this homepage, and not only, I mean, the stiff systems of ordinary differential equations, but you will also find some extra informations. So for instance, the Dirichlet differential equations and the Dirichlet differential equations of, neural types, so on and so forth. And similarly, please try to visit the homepage of Professor Skip Thompson. He's from Radford University back in Virginia, United States of America. You will also get something interesting from his homepage as well about, stiffness and the stiff system of ordinary differential equation. So here is a little exercise. Please try to do it. So try to understand, the stiffness ordinary differential equation with the help of, stiff and non-stiff ODEs solver. So I mentioned a list of the solvers. So you have to, apply, let's say, these solvers to understand, what's going on with, stiff and non-stiff ordinary differential equations. Okay. And also try to understand, the Lambert W function, and also you have to, use, let's say, the matrix 1 norm, matrix infinity norm, and the matrix Frobenius norm in order to, understand the stability conditions for the system of stiff ordinary differential equations. So, for instance, I mean, if I go back. Yeah, for instance, over here, I mean, I have used, the matrix 2 norm, I mean. And why? Because, the matrix 2 norm, it has a deep relation with, the spectrum of the given matrix. For instance, what will happen if you use matrix 1 norm, I mean? I think you will get maybe a slightly different result, okay? And similarly, if you use matrix, infinity norm or the matrix Frobenius norm, you will get different results. Okay. So please try to understand that as well. Okay, so this is what I want to say. So thank you so much.